about what you might call an anti-pattern, which shows itself in so much interesting codage and so much ubiquitous codage that surrounds us on the internet. We started applying basic language theoretic principles to analyzing vulnerability as of, depending on how you count, 2 years ago or a year ago, when Lance Esseman and Meredith Patterson presented their bag of attacks on X509 that started it off. I was looking at the practice of exploitation as a practice of programming of machines that are inherent in targets and are in fact automata that you encounter in language theory all the time. And this came together. We gave a talk at CCC last year. It is on our website. We recommend it to you as an introduction. Today, we want to follow up with our practical examples of all vulnerabilities that express themselves and may actually come from the linguistic effects in data, from the effects in data formats that have non-trivial complexity in the language theoretic sense. And of course, this is an early effort. This is our beagle. We are going to sail to strange lands and collect specimens of strange species, and we hope to build enough of a collection to start a cladistic classification of insecurity. When you see so many examples of how things go wrong, a generalization should follow. Only so can you understand the common origins of all these species and the internal connections between them. So these are the early dispatches from the beagle.
Right, so during our 28C3 talk, we introduced the term shotgun parser. We pointed out that interspersing the recognition of data with the processing of data leads to the actual parsing logic being scattered throughout the code, and therefore, from a refactoring standpoint, comparatively often rather difficult to isolate into code which provides a proper separation of concern between recognition and processing. And very shortly, we'll be looking at some very practical examples of what happens when that boundary gets confused. We're going to be talking about it as a syntax versus semantics boundary. So recognition has to do with syntax. The processing of that data, once it's been correctly validated, is a matter of semantics. And when the two begin to blend, this is where unexpected results start to come out.
So, in these early dispatches, we bring you old stuff. Old, but incredibly famous, as you will see. And the rationale for this is, when you look at software that's just written slapdash and not particularly trusted by anyone, analyzing it is not interesting. You want to look at the errors of experts, not novices. Furthermore, you want to look for bugs that took years, in some case a decade, to find an exploit. Because again, the intuition of an attacker is something that is extremely valuable, and we're convinced extremely close to theory. The question of what computers can and cannot compute has been discussed at the very theoretical end of CS from Church and Turing. On the other hand, the hacker community has been exploring it with respect to each honed platform, going beyond the models and finding the actual limits of computation on day-to-day systems. So we're going to look at those samples, and in each and every case, we will show that something data format complexity, something about the input language may have been what was the undoing of the trustworthiness of the security of that code. Bugs or other cogs of weird machines programmed by those exploits were there not for some random reason, but for the reason of a particular feature of a data language that the programs were supposed to recognize safely before acting on it. And so here is a recap, a very brief recap of our LangSec way of approaching the analysis of a piece of software. You've got input, and then your program separates into parts, roughly. The recognizer, where you're checking input or validating input, or whatever you'd like to call it. And this is where you're expected to be paranoid. This is where you're expected to check all possible conditions that may slip through. And then at some point you have to actually do the work. And this is the processor. And they are separated by this boundary, which is tenuous. People don't usually think about it too much. But when they do and want to prove things about it, they call it the contract or the specification. Or mostly it's just the expectations. There is the beak that goes at the food and is hopefully right for the food. And then there is the guts that take care of processing the data. And you really expect that the data is crushed up in safe little chunks when it reaches the gut.
And bear in mind, what we're saying here, what we're referring to when we say a recognizer here, really is the input handler. If you write your input handler to just accept, a raw buffer, maybe that's okay for the contract that you have with the processing part of your code. If it's not, then we've got our fruit-eating finch chowing down everything from insects to sticks to depleted uranium, and what ends up going on in its guts is not going to be happy when it comes out.
Not at all. This is the rumbling of the weird machine, and it is otherwise known as spoilage. Your expectations are not satisfied, your code exposes a write or a read or a memory corruption or an integer overflow, and moreover they chain up, because this is what the digestive system does, it chains things up. This is what processing logic does, it chains things up. And you chain up an arbitrary computation that you never really expected to perform. So you have to bring the right beak to the fight, to the food, sorry. Or you have to bring the right weapon to the fight and the right beak to the food. The recognizer is that weapon. This is the thing that is responsible for your system security. This is what will allow you to crash up the input properly, or to safely reject what you shouldn't be introducing into your system. And by the way, the tool using Finch is real. It was one of the Darwin's finds on the Beagle. So we're going to talk about two cases of a recognizer not being up to its job. And then we're going to switch to the hairiness of C and the buffer overflows and shellcode and stuff like that. The two examples we're going to talk about are the Reddit comment bomb and then the most epic fail of 2010, which got the pony for that, the anti-cross-site scripting in Internet Explorer 8. And we'll see that in each one of these cases, a wrong weapon was brought to fight, a wrong beacon was trained. The recognizer is a recognizer. If somebody is telling you that you can do away with fully understanding your input, fully checking it up to your specification, instead you could just perform sanitization. Well, this is a myth. We're not going to dwell on the magic codes of PHP, but this is this is the fundamental example of having to be a property of the language that you're enforcing. You can't merely just suppress, substitute out bad stuff. Your expectation is a language property. It should be treated as such.
Now, I want to draw a quick distinction here between trying to suppress quote-unquote bad stuff and trying to enforce a strict separation between code and data. Dan Kaminsky's 2000, I can't remember if it was 9 or 10, but his project Interleak, which was kind of a poor man's monad approach to marking data as tainted in PHP string interpolation in order to submit SQL queries more safely, so that you can tell, okay, this bit of this chunk of data that we've wrapped up here is the user input, and so we're just going to carefully wrap it up in a little box that can't be opened until it actually gets to the receiver, which then can ensure that it hasn't been tampered with. And Interleak didn't quite go that far, but it was well on the way towards that. My point being, the monadic approach is not an attempt to suppress, it is merely an attempt to flag. You're not transforming and then untransforming, or transforming and then further transforming, you're just indicating it as such. And it was a transform-untransform that caused the Reddit comment bomb, as we'll see in just a moment. But yeah, so this comes down to safety and liveness properties. A safety property is you are guaranteed that X thing will happen. A liveness property is you are guaranteed that X bad thing will not happen. So in this case, there's the liveness property of data has not been tampered with, and we'll see that this actually does not hold for Reddit, or it didn't in 2009.
And if you really believe in input sanitization, it's not the beagle, it's the laws build that's going to be. And it's not going to be great. So, a pervasive myth is that escaping is just string replacement. You throw in a regex bitted, you're done. Proper escaping is, in reality, a language property. You should write an automaton to express it, to accept it. You should make sure that this automaton recognizes that language. This is what Reddit did. They wanted to prevent double escaping. So when they escaped a character, they replaced it with an MD5 of that character, dropping down those rather large chunks in. And then at the end of the substitution, transformation, computation, they replace them back into the original form. And of course, the moment this occurs to you, you think, what if I put the MD5 in the input from the beginning, from the start? So maybe the the substitution system will substitute it in the end. So when you are handling that string of characters, you are already dealing with a language accepting automaton. You are dealing with a rewriting system. And what comes in comes out. You can drive computation that way.
This is also what gives me the willies about rewriting rules for things like JavaScript. Kafka is a pretty cool project, and it's doing some neat stuff with object capability security, but the rewriting really does give me the willies.
And what completed this circle and built scriptable command bomb was another markdown feature that allowed the user to define variables to get substituted. And so these two things feeding into each other allowed you to escape your JavaScript with your pre-supplied MD5, which was helpfully converted to your original that you wanted to perform. And then on mouse over, it would cycle over and over and over again, and you would automatically post comments on Reddit. When you complete the circle, you usually need a loop and an if, and then you have something that is pretty much your standard Turing machine, your standard program.
Labels and branching conditionals, that's all it takes.
But it gets better. Oh my god, it gets so much better. The IE anti-XSS feature followed the no-script approach, except Microsoft thought. So we're seeing this request going out to a server. Let us match things in that request, and let us rewrite the response of the server with regexes. As it comes back from the server, if it looks like it's trying to do cross-site scripting. So we're going to watch the input, generate some patterns for the output, and correct the output, break the output of the remote server. With regex like this, the letters in braces were replaced with a hash mark, presumably breaking the HTML logic. Now, HTML and generally the structure of web pages is at least context-free. It's recursively nested. You bring a regex to validate something or to operate on something that is recursively nested. What do you get? Pretty much.
This is Dejector from 2005. You know, you need to be using context-free validation in order to validate a context-free language, and if you instead decide to try whitelist with regular expressions, the pigeonhole principle is going to end up biting you, and you end up getting exploited. It's just in HTML rather than in SQL.
Regex are good for things that nest to finite depth. You go one level deeper, there's absolutely no telling what you're going to rewrite. Now, since this is coming from the remote server and is affected by the outgoing requests to it, you can manipulate this rewriting system every which way, rendering perfectly safe sites vulnerable with your anti-XSS protection. And who saves you?
Believe it or not, Google actually switched off IE8 XSS protection in the Chrome extension for Google Docs. So you can actually avoid this problem in Chrome, wait. Yeah. Oh, that's right. Yeah, they turned off Google Docs. Well, yeah, it has nothing to do with Chrome extension. My bad. But yeah, no, they shut that bit off, and suddenly, suddenly you can't get pwned by this anymore.
Because basically Google tells you, hey, this XSS protection thing, don't do it. That extra computational engine that actually rewrites your page on the fly in ways that your server cannot appreciate, just don't do it. And it was the worst fail of 2000, or a defensive measure in 2010 as awarded the pony. This is very important. You bring the wrong kind of computational engine to the recognition task, to the data validation task, it will become a part of the exploit mechanism. It will be borrowed to actually make your actual application wrong. This is a general pattern. Now, if you haven't seen the Mario Hydra's Got Your Nose talk, this is how no JavaScript, just the cascading style sheets and HTML5 SVG tags can have a party in your browser. This is how your passwords, helpfully filled in by the password manager, into a rendered element with CCS every time, can brute force your password and send it up to a remote site. Again, if something breaks the loop,
this is shades of the proof that HTML5 and CSS together without JavaScript are Turing complete. I mean, the exploit that does this doesn't actually have to be Turing complete. It's sufficient for it to be a linear bounded automaton because it's doing a fairly simple task. But yeah, if this doesn't frighten you, you don't need to be in web application security.
If something brings repeated substitution, and the substitution can distinguish between two alternatives, chances are you have at least a brainfuck automaton.
Yeah, because if you can provide input to some loop, if you can control that input, then if recognition and processing are interleaved, then you can drive the operation of that loop with a specially crafted input.
So this is to say, a recognizer, a rewriting system is already there. Your data is already being transformed as it is being consumed. A computation happens before you even start making. It happens before you have fully loaded your program. In another talk of ours with a student of mine, we look at relocation and loading of Elf binaries and show that even before any binary code is jumped to, there is already a Turing complete environment that is driven by nothing other than the relocation entries that enable you to do ASLR and shift pieces of code back and forth, and a dynamic symbol table.
This was the brain-fucking ELF metadata talk from this year's DevCon with CERT and Bex.
So, there is already a rewriting system. You have to control it. You have to match it in what you do.
You have to be certain about what input is valid and what input is not valid. You have to recognize the good input and reject the bad input, and only process what you can control. So now we're going to take a look at several binary specimens of finches that dropped root shell. One in Bind, one in OpenSSH, and one in OpenBSD. And we're going to talk about software engineering principles that could have helped patch earlier on what was, what later turned out to be a root shell level vulnerability. These are best practices in the industry that, to be fair, are not as formal as we would like. We're going to be getting into like the Bertrand Meyer, Kent Beck level of like really classic software engineering recommendations. But this is all stuff that this is all going to be about patterns that you can recognize in your own code as signs that you need to look into refactoring out a separation of concern between recognition and processing, between syntax and semantics.
Because we've scared you enough with thou shalt have a proper recognizer. But let's look at those classic pieces of software that have been serving the community quite well. Actually, I have to go back one slide. Bind. Despite its reputation for bugs, it's the glue of the internet. OpenSSH, a TCP IP stack of the most security-aware Unix distribution, or one that certainly strives to be such. And we're looking at pre-authentication bug in that. And a remote code execution in the other. Isn't this something? I mean, if you can't trust this, what can you trust? If you can't trust these people, who can you trust? We hope to convince you that what caused these bugs to happen was that people have made not free and easy, but just a little bit more relaxed with the data format, or a little bit more complex with the data language.
And to be honest, there are places in the code where they admit it themselves. You're about to see one.
One concept that is central to all this is going to be context sensitivity. When you're looking at a piece of data, when you're writing your small functions to process a piece of data past the recognition stage, you want to make sure that you can validate this piece of data on its own, or that you have the right context to see if it actually makes sense. This snowballs. The more context you need, the more context the language structure of this input, say, offsets, back references, compression, length fields. The more of this you have, the harder it is for you to validate context-sensitive data. So, the year is 1999. The Beagle is traveling in the past, and it turns out back then that in DNS, it would be nice to be able to say, this name doesn't exist, but it would exist between these two names which do. And this could be a sign assertion. Signing an NX domain, one-bit response, no, I don't know this name, is silly. Assigning this record that says, oh, this name would fall between these two, which are defined, but it is itself not. That is signable. You can sign such a record. And indeed, there was a new type of record introduced into DNS called NXT, given by these two RFCs and included in bind. And it worked something like that. You could ask the name server to retrieve it. If you exploited an authoritative name server, you could have your target name server retrieve that record and get code. And the implementation of that NXT record was bugging. So that was T66 by the EDM crew was the exploit. So you could go about exploiting name servers on the net if you control one authoritative one that you could bounce queries off of. And before we go into the code and look at it, and look at the pattern of parsing that made this possible, keep in mind that DNS is context sensitive, and DNS format involves a length fields. So this is your typical DNS packet. There is a standard header, query ID, flags, and then counts of various RRs, resource records. So there are 4 RRs here. What RRs do for names, for substrings, is they refer to previous RRs by a offset, negative offset, back in the packet. Having spelled Linux.unixwiz once, you don't want to spell it again. You just, in the RR, put a back reference to that string in the packet.
Now, I want to point out from a parsing perspective, if you've looked at Hammer, which is the packrat parsing library in C that TQ and I wrote earlier this year and are still working on, one of the things you can do with Hammer is you can say, all right, read this value and use that as the number of times to apply another parser. So if you architect your parser so that you have essentially a general parser for a parser for all possible types of RRs, you can read the number of RRs, apply that parser that number of times, and you're fine. But that's not how most people tend to do it.
Context sensitivity and length fields. So remember, if you have a shotgun parser, Mr. Length field is no longer your friend. This is the layout of an RR, And what is to notice is that the first 4 fields are fixed length and fixed interpretation. The 5th field, RD length, is the length of the R data that follows. The length, the content of our data that follows is in fact a domain name for this record, and this domain name may contain big references.
We actually have an example of DNS. It's not complete, but it does go at least this far. On the GitHub repository for Hammer is the examples directory, and so you'll see that for the RD length our data field, the parser basically says, okay, RD length is the number of octets to read. Grab that many RData octets, and then apply the RR parser to that buffer.
Now, think of validating this kind of a record. What do you need? You need the context of all of the previous packets. The domain name is compressed. It can only be checked after it's been expanded. This expansion must be consistent with your buffer. Your processing code is something that will create that buffer, will have the contract, will expect the validity. This is what the code looks like. There is a switch up above on the type, on the integer type of the case. And this GN expand will expand the name into a canonical form, retrieving all the previously saved strings. And so you go checking that name, and you need to eventually hand it off to your processor, and here is an MCPY. Guess what happens? You don't know the length of the string that you're going to end up with. You could, if you were doing a correct recognizer, completely compute that length first. Make sure that the length in the previous packet matches, and only then commit to copying memory. Instead, look at the str length in there. You are copying this data. You are building up your substrings for further expansion based on what comes in the input, not having validated the packet. MCPY corrupts memory.
I mean, literally, you're just jumping, you're creating a new buffer, essentially right at the end of the other one, and just copying straight into it. So, I mean, it should be obvious that one can clobber the other.
This is, and the reason this happens is that the data structure, the data format that you've committed yourself to, has subtle restrictions, subtle validity conditions on its length fields that occur throughout the data. It must be computed as you parse the packet. And if you haven't recognized the packet fully, well, don't copy things into memory.
You know, one thing we've noticed is that when this particular pattern of, hey, let's put two things right next to each other in memory because that'll make the reads faster. Good intention, but leads you to having one buffer end up clobbering the other for some reason or another. We'll see. We've seen this here, and we're about to see it again in the IPv6 example.
So having failed to properly validate the context-sensitive length gives you too much of a str length, gives you the control. Beware of context-sensitive data formats. Elements that must add up with their length fields across a long span are a temptation, they're danger, they're a sin. You can't go parsing the packet and working on the data until you've totally confirmed that they all end up. This is the type of that struct. This is the meaning of that struct. You should recognize it fully before you commit. And this is the story of the OpenSSH pre-auth. which rocked the world in 2002 by way of globals. You should study that exploit. This is the simplest parser you can imagine. Here is a really well-formed piece of code. Packet get int. It eats 4 bytes off of the buffer that is the incoming packet and moves a pointer into that buffer. It's very, very simple. Look, first you eat up an integer, then you eat up so many strings, and each string starts with a length. These are Pascal strings. This is how the packet get string works. Consumes 4 bytes and consumes so many bytes following it. And notice something. For this packet to be valid, you must have the number of strings, number of challenge authentication responses. That number and rest should be exactly equal to the sum of all the characters that are in the strings. So you are looking at the string, and here is an integer that should add up with these integers, right? This is what makes it valid, nothing else does. Packet check end of message actually kills parsing if the lengths do not match.
So at this point you might be wondering what's going wrong here. This sounds like exactly what they've been advocating all this time. But dig a little deeper,
and you'll see that there is a problem. The problem is that you are doing the memory allocation before you validate this condition. As it happened, this is susceptible to an integer overflow. And the way it was fixed, random restrictions were placed on nrest. But the integer supplied in the packet was too large for the rest of the packet, was not rejected, because you only reject when you check the end of message that you've consumed all the characters, there is no extra garbage, there is no truncation. But by that time you already copied memory.
And that's really the subtle parsing error there. They check the condition of what happens when we finish parsing and there is still data left. Well, that's obviously invalid. What they're not checking is what happens if we run out of packet before we're done parsing.
And so the xmalloc length was too short. That gave a memory corruption. Goebbels did an amazing job leveraging that memory corruption, but basically once that memory corruption is there, you are sort of screwed. Now, actually, how do you have time? 20 minutes. We're going to look through, we're going to walk one actual Emacs buffer, and then maybe we'll look at this code some more. The boundary between syntax and semantics is kind of tough. When you see special cases in the code that have an integer, such as an offset, represent something different based on context, based on why it's passed in, that really means that your input format as a language has this special, interesting feature which you are probably not handling right. The proper intuition for this is code smells.
So Martin Fowler wrote he wrote the book literally on refactoring. And in that book, and in a lot of work that has followed on in software engineering, as a discipline, there has been developed a taxonomy of code smells, which is to say things that, if you see this in your code, you should say, is there something a little more interesting going on here? Because they don't necessarily signify that there's something horrible here. The C2 wiki, which we're about to refer to heavily, makes the point that there are purists and there are pragmatists when it comes to code smells. And a purist will say that every code smell needs to be eradicated from your code. The pragmatist will say, no, a code smell is a signal that there may be something funky going on here, and code smell should be investigated, but if it turns out that nothing's really going badly, then you don't necessarily have to do anything about that. Now, we'll make the case that the OpenBSD team thought that their code smell was okay because of what they were intending to do, but they missed a subtler point. So you'll be able to decide for yourselves when we're done whether the purist or the pragmatist approach is better here.
So the year is 2007, and this is the IPv6 remote kernel stack buffer overflow. This is big. This is
of death.
Yes, this is the biggest one of them all. And this is actually arbitrary code execution as well, as of course Ortega and Hera were able to show. And this is IPv6, right? This is a pretty complex protocol that gets rid of some of the complexity of IPv4, but adds this linked fields and chaining of options. So IPv6 is very much a language theoretic phenomenon. You add only those headers that you need, and the place of those headers and the meaning of those headers is determined by the next header field. So if you remember IPv4, there used to be some fragmentation CRUD in there, which eventually just converged to, hey, fragmentation on my network. Somebody is doing reconnaissance, or somebody is doing IDS evasion. Why don't you shut this down now? In IPv6, fragmentation was removed. It's now not the router's responsibility. A host may fragment its own packets, but the router wouldn't do it for you. And if the host needs to add some fragmentation, well, so it will. It will include a header, an optional header, that will carry the fragment ID and length information, and the next header will point to it. And so are the headers chained. You see the next header here is the upper layer header for, say, UDP or TCP payload. Here, there are some hop-by-hop headers, extension headers that may be fragmentation headers, and only then an upper layer header. And they're all dispatched on this integer field, which is just the type of the header that follows. Now, this was the packet format. Let's look at the data structure format in which these packets are kept. One claimed success of OpenBSD was the performance of its MBUF scheme. MBUFs are 256 chunks of memory where packets are kept. Each packet that is longer than 256 bytes of memory can be kept across a chain of MBUFs. So the first scheme you see here has the obligatory header for each chunk, the M header, and the flags in the M header would tell you, is that the first packet, the first fragment of a packet? If yes, then it will be followed by the packet header, the second data structure here. Or is it a data store? So if the flags, instead of indicating that this is a packet header, say that this is a data, and it points to this cluster of MBUFs, then you can see a packet with 256 first bytes in the data, and then the rest of it in the MBUF cluster, and it's a union, so the extension header, the little extension header, MX, points at the storage. Interestingly, it also points at a free function. It contains a function pointer that will free that storage. Now, you're thinking, if you manage to overwrite a function pointer that sits right next to the data of the packet, what can you do? And the answer is yes. This is how that vulnerability was actually exploited. It took a whole lot of work untangling that function pointer from the rest of the kernel code and then being predictable and then exploiting it. But the potential for overwrite is there.
Those of you who are object-oriented nerds are probably already a bit squicked by the fact that the mNext pointer in the header of one mbuff is pointing directly at the header of the subsequent mbuff. I mean, that's like a serious violation of boundaries in proper design. And you know, this is C, people do that. And this was done for efficiency reasons.
So you see there are two languages fighting each other. One, the language IPv6 packet, the complex one, with optional elements and variable lengths. The other, the language of mbuffs. So what happens is, packets are stored in chains of those mbuffs, and before they are recognized, before you, for example, ascertain that the ICMP packets, fragmented ICMP packets, are in fact valid, you already copy them into those buffers, and you operate on those buffers, changing them in place, and I will show you the function that does that.
So what's going on here is basically, it's like, you know, recognize an option, process it, recognize an option, process it, recognize an option, process it, and it's this interleaving that's causing this problem.
This is extremely context sensitive. And look, when you operate on a packet, you want the bytes to be in a row, not spread across the two mbuffs. So you have a simple function called mPullDown. And this function ensures that this stretch of bytes of the packet payload, offset to offset plus length, is continuous. It will allocate another mbuff if it's not contiguous and allocate it there.
And so if an mbuff gets allocated right next to the previous mbuff, which is still being written into, and the thing that gets written into that first mbuff is too large, where does all that other data go? Directly into the next mbuff, of course.
And, you know, over the bridge and into the river, that is to say the function pointer. This was a special case of the function that performed the buffer overflow. Look at this comment up there. In fact, this function, dup1, is called when the bytes are contiguous, but the author of the code wants to say something by the fact that the offset is not at the beginning of the buffer. So this function, mPullDown, was being used to communicate another bit of information that turned out to be related to how fragmentation was handled, fragmented headers were handled. You see a special case. You see a strange language phenomenon that is being communicated about. This is where the buffer overflow actually happened. Now, let's look at the structure.
Okay, so the function that OpenBSD uses in the kernel to handle an IPv6 packet, Sergey is going to show you just exactly how big this sodding thing is. I mean, this is a nearly 500-line function. I mean, that's nuts. That's ridiculous.
So this is the very simple interrupt handler that grabs the packet. The packet is already split into those mbuffs. And it's being dispatched to IP6 input. So here is IP6 input. Now, this M flags and X, this is already your mbuffs. M is your mbuff. And you start parsing your packet. So is this packet of the correct length? You're recognizing the packet. Is this packet of the correct length? Does it have a buffer? Does it have the right version, IPv6?
Blah, blah, blah. We've got about 10 minutes left, so let's get back to the slides rather than walking through this entire giant function.
Yes. Just one more second. So you see, this is the recognizer. This is the recognizer. This is the recognizer. How much memory allocation do you think it already does? In the process of this recognizer, you see this ICMP6 error. That's when the error is being sent back. This is your packet being rejected because of some condition that's wrong. And it just goes on and on. And throughout this, it is operating on those chains of mbuffs using the data supplied by the packet. This is the hop by hop rewriting, and it just goes on and on and on. And in the end, it's finally deciding to reject the buffer. And what does this end with? This ends with this wonderful comment. More sanity checks in header chain processing needed. You bet they are.
Right, so this is a code smell. If you print out the function and it is longer than you are tall, you are probably doing it wrong. So the pragmatic approach suggests that we want to look more closely into this and see what's going on. Well, that piece of code certainly has more than one responsibility because it's doing a whole bunch of recognition stuff and it's doing a whole bunch of processing stuff. You know, so Bertrand Meyer was talking about object-oriented programming, so that's why he's talking about classes, but functions, this is the case for functions and bound methods as well. If a function has more than one responsibility, that can lead to problems. Bloated code is hard to read in the first place, but it's also very difficult to tell whether it's doing just what it should and nothing else. Now, I think what they were trying to do here was they were trying to honor the principle of composition, which says that you should keep everything at the same level of abstraction. And IPv6 is a layer, right? That's part of it's part of that layer of the network stack. But as we've been saying, the syntax of a layer of the stack and the semantics of a layer of the stack are different sublayers within the overall layer. So they're just at slightly too high of a level of abstraction in order for this method to really be the right thing. What they should do, or should have done, is extracted the separate parts out into separate functions so that we can keep track of what's going on here. That's not what they actually ended up doing.
What they ended up doing was they took a function whose responsibility was being a recognizer and thoroughly cross-bred it with the processor, router, forwarder. They were very, very good. We're talking about the OpenBSD team. They just don't take anyone there. They probably wouldn't take me. But in a number of cases, they had language issues connected with length fields, fragmentation, and context sensitivity. And in one of those cases, just one, maybe, they didn't quite do it right. And the result was pwnage.
So when we say offsets, we could be talking about offsets into a packet, which is a syntactic issue, or offsets into a buffer, which is a semantic issue. And when you have one packet equals one buffer, then you're fine. There's a one-to-one relationship between the two. But in the fragmentation case, or in the case of packets whose data is more than just one buffer, you don't have that guarantee. So here's what they did to fix it. And there's actually another code smell here. So as you see, they've inserted a special case here. Now, when your code starts to handle lots and lots and lots of special cases, what this says is that you tried to generalize, but you had to add a bunch of exceptions to that generalization, so maybe your generalization wasn't quite as general as you thought it was, and maybe you need to look at how you're doing your generalization again. That's the arrow anti-pattern. You're adding a whole other level of nesting. And again, this is something worth looking into.
So you see, let me show you something. I'm going to show you the macro that actually reallocates the buffers and pulls the M pool down, right? This is a macro that operates in the middle of the recognizer, allocating memory, sewing up and creating new M buffs, okay? IP extender yet, okay? And now, let's see this. Let's see how frequently it occurs in the stack. Look, it occurs all through the stack. And look at this. Where does it occur the most?
ICMP6, which is in fact where the problem ended up being. The attackers were able to generate a flow of fragmented packets, and about 1 in 100 packets dropped root shell. And the semantic ambiguity with the use of offset as a language clue as to what the packet, what the buffer meant, was the undoing of it. So isn't this interesting? This is how one of the most, because of this purely language theoretic issue, one of the most resilient stacks was owned. And might, for all we know, we're still investigating just how serious the problem continues to be. Expect more soon.
Read the paper on the exploitation of this vulnerability, and you will see that the geniuses who exploited this at core actually couldn't be bothered to trace the path to the particular vulnerability through the stack because it's just so complex.
We think they probably found it by fuzzing. Because of the extent to which fragmented packets can be reduplicated in that particular code path, ICMP6 was particularly vulnerable. But we need to, now that we've traced this back to what we're pretty sure is the root cause, we need to validate that, and we may be having a conversation with Theo fairly soon.
Yeah, but you see, this is really interesting in that most of their work went into composition of the exploit with the rest of the kernel and patching up what was broken, which was absolutely brilliant and is classic hacker application of composition of kernel architecture. I always give that sort of thing as an example in any advanced OS class that comes my way. But it's interesting that this was probably not found by a top-down analysis. And it could have been, and it could have been found from the sound possibly. Yeah.
So as we conclude, I want to remind you all that these are just early dispatches from our survey of the taxonomy of exploitation. We're going to be spending an awful lot of time in the coming months with OSCDB, re-examining existing vulnerabilities and looking at other examples, possibly in the same code bases that those original vulnerabilities came from. Because if it turns out that these patterns are as pervasive as they've turned out to be in OpenBSD, we may be able to solve entire large swaths of bugs at one fell swoop. So we're pretty much out of time here, but we will. When is the workshop that we've got?
This is a good question.
Okay, it's somewhere in the schedule. We'll sort this out at some point, but we will be spending time. We'll be spending we've got a 2-hour block tomorrow to work on exactly this sort of stuff. So if you're interested in hopping on the boat and helping us discover new species, new taxa of exploitation, please come join us tomorrow. We would absolutely love to have you. Do we have time for questions, and if so, what are they?
And hopefully we have convinced you that these particular kinds of highly impactful exploits, bugs, in highly professionally written code, all go back to the violation of the basic language theoretic principles. Recognition should complete before you start processing. If your language is context sensitive, you should beware such data formats, working on such data formats, before you validate them. If you have a chain of lengths that should all agree, you should ascertain that first. Only then allocate memory where your other important data lives. Otherwise, chances are it will get corrupted and overwritten because you are dealing with data that you have not validated. It may be too late to free up and discard that buffer by the time you figure that something went wrong and there is some mysterious byte garbage all over the place.
Yeah, it would be a shame.
But first and foremost,
network.
all of these examples come down to data languages. Data languages which were a tad stronger or a tad more fast and loose-handled than they had to be. And when recognition fails, the contract is violated, the processing will lend itself to unauthorized computation, unanticipated computation, weird machine pillage. We have the code. You're welcome to join us and pore over that code, or completely lambast us for saying these things and say, hey, but how can you parse without allocating memory? And hopefully we'll be able to satisfy you that there is a safe way to do that. We'll point you to the hammer talk.
All right, thank you.
Okay, first a couple of announcements. After the lunch, there will also be workshops